guys are interested, we're going to do a quick defense in depth Bitcoin talk, specifically focused on trusted execution environments. You guys will hear a lot about this in the next 6 to 12 months. OpenBit, what is OpenBit? Cbook is napping maybe. His company has a white paper where they discuss, they built an entire, I'm going to let him talk about that tomorrow. They've got
something cool though.
Something cool. They got something cool they're going to talk about tomorrow. But specifically today, we're going to talk about trusted execution environments. But before we do that, I'm going to fix my clicker. We're going to talk about the major types of trusted execution environments, the challenges in developing on top of trusted execution environments, and then discuss remote attestation, like how do you remotely attest someone's trusted execution environment. And what I care a lot about is decentralized attestation, which no one's talking about yet. But before we get into that, let's talk about defense in depth. This is not like a hammer that you just like, and like everything is not a nail that you're just going to use TEs for everything. Although in the future, you'll probably start to see developers just using TEs everywhere. But like this is something that when people come to me, I tell them not to do it. It's like a very specific, you have to match, what is the risk of your application? Like what are you trying to secure? If you're just running Angry Birds, the game, maybe you shouldn't shove a virtual machine into an enclave and then try to like remotely attest that.
Because accepted.
There's a
Angry Bird on BPM coming. I played that one.
I know this is a Bitcoin talk, but Secret Network learned this the hard way. There's a cost associated with managing and updating your trusted execution environment infrastructure. If you don't do that correctly, you will get owned later. And so people are already really bad at securing infrastructure without the complexity of what we're going to talk about today. So if you're going to do it, you got to pay someone lots of money to do it correctly, or else you're going to get owned and you're going to get talked about in all the cool academic papers. But ultimately, I want to let developers choose. Like this is not like I'm not selling anything today. Unfortunately, I don't have like a token or like something to make money on. This is like I think I want to create ecosystems and tooling where developers get to choose what to do. Like we're not trying to force anybody to do anything. And the two things that I talk a lot about are insecurity, or confidentiality, and integrity. So confidentiality is like no one has access to the data, and then integrity is it's hard to modify the code and its behavior. And so we're going to talk about, in the context of TE, we're talking about confidentiality and integrity today. Does anyone know what a TE is before I get into it? Has anyone, except for you?
SGX.
Has anyone actually like ran code inside of a TE in production? No, okay. Like all the phones in your pockets today have TEs on them, but the way I like to think about this is like TEs are rising in popularity today, it's particularly in Bitcoin and Ethereum ecosystems for reasons unclear to me. I don't know how this stuff works, I just ride the wave. And the problem is the current architectures and the vendors behind them, it's very fixed. There's not a lot of wiggle room in how you actually use TEs because it's tying you to a specific architecture. And just at a high level, the way I like to think about trust execution environments, whether it's an emulated thing in software or it's just something in hardware, there's this non-secure world. So this is like, you can think about like your mom using her computer. Like that's the non-secure world. Like all sorts of shit can go on there. There's a secure world, which is like what I'm going to call the enclave that you would use to run secure code. And then there's hardware, the hardware itself that links this protected resource to a secure environment. And then these things they don't need to talk to each other, but specifically the secure world needs to talk to some component of the hardware. And we're going to explain why this is. So this is kind of the way to think about it. There's like, this is an old school way to talk about TEs. This is secure world, the non-secure world, and then your hardware.
So do you remember like when Helium launched the IoT miners?
No.
Oh, okay.
I know they did that. I got an ad to buy their new thing.
Oh, no, but I know that there was like security issues because you had to connect the miner to your actual like home like router.
Yeah.
And then, but it was also like, so it's connected to your home router, and then it's also like in the IoT network. So it's like everyone could potentially have access in, and they were saying that it was something in the hardware that like was the security aspect.
Yeah, so this is where like the defense in depth thing comes into play because there's so many levels of
protection.
Yep. You're doing like isolation at the network level,
yep.
or isolation at like all sort of like the old OSI stack. Like how are you doing that?
Yeah.
And so this is specifically talking about, we haven't even gotten to isolation yet. This is just talking about how you actually, like this is building the root of the entire system is in the hardware.
Okay.
And how we do that, there are a bunch of different types of trust execution environments. I linked this in the Telegram group. There's the academic TE, which PhD types love to write about. You probably have seen Keystone, maybe, if you're following the crypto TE space. That's Don Song's RISC-V TE. Don Song has an ERDOS number of like -1. And Google had to follow suit. Google has something called the Titan M, which my Pixel here has the Titan M chip running on it. And so you can think about it here like your phone in your pocket has a bunch of hardware, right? And there's some part of your hardware has a protected hardware resource. I'm not going to get the details of what that means today, but we're going to explain how this links together. And so you can tell there's many different types of TE. So when someone says, like, I want to do a TE, you need to ask them, like, what are you talking, like, okay, let's talk about it, what is it? And there's two major types. I'm going to break it. No one talks about it like this, but this is how I'm going to talk about it today. There are whole VM TEs, and there are enclave TEs. And a whole VM TE is when you just shove an entire virtual machine into what you would consider a trusted environment, whereas an enclave is supposed to be the smallest amount of code you can create. You put it into a trusted execution environment. And so an enclave is supposed to be like, I'm going to generate an ECDSA key pair, and then maybe I'll like sign some data and have very like small attack surface, a small narrow interface to do that. Whereas the whole VM is just like, let's just spin up Ubuntu, let's just run, just like the Bitcoin, like let's just run Bitcoin D or whatever, and then we're just going to like attest that entire code base. So the difference between these two, like we talk a lot about trusted code base. The trusted code base in the enclave is much smaller because there's less code, whereas in the whole VM, you're like, it's insane. Like I don't even know why people are doing this today, but developers want it, so we're going to give it to them. And so whole VM TEs today, Intel TDX just launched about 6 months ago, and Android will eventually launch publicly something called the protected KVM on your phones. And so it's effectively a hypervisor that allows another virtual machine to have encrypted memory access and protects from another virtual machine from accessing that encrypted memory. And so the PKVM code base that Google uses is all open source, so you can actually check to see how you implement something like this, because everybody just stole from KVM, like AWS and everybody else. So it's just a hypervisor that protects access to, in this case, MicroDroid is the operating system that runs in the virtual machine using this protected virtual machine firmware that is signed and attested to by the hypervisor. But this is like more research oriented, like people, I don't know any companies running virtual machines in enclaves yet, but you're about to see it in the Ethereum ecosystem about thousands of services using this in EigenLayer. Just because it's really easy to like run Ubuntu and then run shit in it and then just shove it in this environment and just say like I'm doing this secure thing. We'll hear from him about how these guys are doing it tomorrow. And then this is the most common type of TE, the enclave. And the way you can think about this is we call it a library OS, so it's a very small version of operating system that's only designed to do a very small amount of things, like create an ECDSA key pair. And so there's popular open source applications that people use today. The most popular one, the one I like to use, is Grameen. It's funded by a mafia called the Confidential Computing Consortium. Everybody's in it except for Apple and Amazon Web Services. Aplum is also very popular. Scone is a research library that got a lot of popularity. And the whole idea is they provide standard libraries that allow your app, let's say you're programming in Rust, to access like a random number generator or like malloc or like file system handler access. So they provide these convenience functions for you, but it's not a general purpose operating system. You're not going to be
watching YouTube videos.
You're not going to be watching YouTube videos. And so the trusted code base is much smaller. But there still is a reliance on this hardware interaction between the secure world and the hardware itself. So this is what I use, Grameen. And then really quickly, just to cover the whole spectrum, what people really want to do when they talk about trusted execution environments is attesting those environments remotely. So effectively, you can think of RA as the ability of a verifier, or remote verifier, to query a prover's enclave and say, like, I want a report from you, show me what you're running, and then that report attests to the code loaded in the enclave. I'm gonna explain how that works, but you can think about, this is a prover, and the prover is running a quoting enclave that is from Intel. So Intel actually wrote this. Intel's running this thing inside of a chip that you don't ever see. This is like a magical fairyland that they create this thing, and it has access to specific hardware that leaks keys to it only to do the quote verification and generation. And so the challenger can actually force the quoting enclave to create a quote for the application enclave. So like, let's say this is running BitVM. I'm the challenger, I want to say, like, show me, like, what is the quote of your current enclave. Intel has an enclave loaded that will help create a quote or a measurement that is signed by Intel, and the challenger can get that quote out of a running enclave. It's like a high level way to, I'm going to explain like the trust assumptions in that model, but this is how it works at a high level. You've got essentially you have Intel, you've got an adversary, and you've got yourself. But it's important to remember that this whole architecture was designed for DRM. And so like the user's devices were the malicious, we are the malicious ones in this, in this environment. And now it's kind of flipped where like we are trying to write servers and software using the same architecture. So the way it works, I'll go back to that quote. This is a weird Intel diagram, but there's essentially three owners of cryptographic material in this ecosystem. There's Intel, the keys that Intel manages and owns. There's your cloud service provider or your decentralized service provider, and there's you. And so you can see on your own processor, everything in blue is owned by Intel or signed by Intel keys that we just implicitly trust. And so if you don't trust Intel, there's a driver signed by them. There's this ECDSA quote generator library, which is actually an enclave itself. And there's also the PC, like the keys themselves that Intel provides that your cloud provider hosts for you that are running on your chip. And so part of the trust assumption here is if Intel is owned, then Intel can generate enclave measurements that are fake, and then the whole system breaks. And so this is like, I don't know if you guys pay attention to Ethereum, this is like an Ethereum bro, and like this was today or yesterday. It's just like, basically that just means we're trusting a hardware manufacturer if you use a TEE. And so like, this is like what, 2 sigma or 3 sigma out here is me, or maybe this is me, I'm not sure. You're here, but like, you have to trust something, right? And so this is like the trust assumption is like, if you're going to use a TEE, it's rooted in the assumption that like you trust the hardware manufacturer.
I'm confused by the meme. Is he endorsing the Midwit meme, or is he saying like it's bad?
I feel like the problem is I know the background on why he tweeted this. So but like the way I read it first before I asked internally was like he's against. I replied defending it. So
it seems like he's like saying like you should use the TEEs and like basically saying like ZKs are like mid-curving it, like that basically you're like overcomplicating it by using like ZKs and like you should just trust the TEEs, right?
I mean, but the text seems to indicate he's like
he's not surprised.
Well, he's like saying,
shouldn't you know this?
Yeah, I mean, that's also one way to think about it. But like, you guys all use a web browser, right? Your web browser, like when you do web. He's using smoke signals and pigeons to like his Bitcoin block, whatever, starting. But it's the same concept with your browser. Like your browser has a root of trust, which is a bunch of certificates that your browser decided are like good, and the whole trust of the internet is based on that bundle of certificates. So this is kind of the same concept, but in the future you need to be careful because a bunch of people will just assume you don't know what this stuff is and just say this is secure because I have a TEE. Like they'll just assume, oh, I'm running it in the TEE, so that means it's secure, which is not necessarily true. If I had more, there's a whole. I just wanted to like quickly cover this topic with you guys. I'll explain a little more. But one of the big challenges from a DevX, I don't want to get my tinfoil hat on here today because I'm not going to rant about security much. I'm more thinking like a developer. So today, Ethereum pays me to help them build secure infrastructure on top of TEs. And Ethereum does not give a shit about big vendors. They're not like focusing on just do Intel. And so there are many, if you use Amazon Web Services today to host any of your servers, they cock block you from accessing the low-level model-specific registers of the CPU, and they force you to use their hypervisor, which is Nitro. And so the measurements that you'll get when you try to use Intel SGX low-level system calls, you'll come back with some AWS Nitro bullshit. And so you need to write an entire stack that can parse their binary formats. And so you need to like support, and then this, okay, then it's like, okay, we're going to use Intel chips for our Bitcoin nodes, so like we'll just use Intel SGX. But like, well, what if someone has an AMD chip that they want to run a Bitcoin node on? You need to support their crazy encrypted virtualization, nested, blah, blah, blah stuff, which is a whole different trust verification attestation infrastructure. And then ARM's like, hey, well, don't forget about us. We're embedded guys. We've got TrustArm. And so there's a whole different stack to support. So right now we're at the very beginning of this, like renaissance.
Should people use all of them?
Excuse me?
Should people use all of them?
I think his company has in their white paper, they explain that they use multiple versions. They use a bundle of these so that you're reducing the trust
right.
Like reliance on one specific vendor. But that means someone in his company had to write parsers for each of these things, which is nuts. Mm-hmm. And that's the open source. So I haven't seen that. We'll talk about that later. But go back here. I'm going to do my Arabic section. So I have a bunch of details on how you actually do remote attestation, like a little demo, but I'm going to skip that for today.
I saw a slide that said errata.
I know that means error or something. So I'm just gonna like quickly like pause on this. I know I'm like this is a really flash talk I just did 2 minutes. Does anybody have any questions on like TEs or like why you use them or like what's going on? Just try to answer any questions.
So, for example, the secret enclaves on our phones. What's stopping people from extracting them? Is it physics?
Or what is the question?
So what is secure? The secure enclaves on our phones. That's a private key, right? So is it possible for, let's say, Intel to extract the private key? It's just
okay,
difficult.
So that's a great question. So
Intel,
Intel,
expensive, or it's just impossible?
So Intel, when they like in their documentation, they describe the genesis of these systems on their chips. And so at the fab, on chip, which they don't have, I don't have a cool zoom in X-ray like he does for his. I would love to have the same like binary gate thing. Here's your SGX. Here's your ECDSA keeper. Be a lot bigger. They don't actually describe to you the process by which they delete that key material. And so each manufacturer, when they build a TEE, they're burning in specific keys into that chip. And so like what they tell you is like just don't worry, we deleted it. We don't know what those keys are, and it's unique.
Trust me, bro.
There's a room that says like not NSA on it, and they put the information in the room, and it doesn't come out.
But can you read it? I mean, it's a room.
If I've searched GitHub projects for like extracting a key from an Intel SGX, and there are GitHub projects that say they can extract keys from them with like a 90% success rate.
So what he's talking about is info leaks, like side channel attacks on like one of the things we didn't talk about like the like applied use of TEs. People will like generate key like secret network, which I'm not, you guys don't follow Ethereum. They have this like, hey, we're secure, we're in SGX. They generated key pairs in here, and there was an attack on something the way that they were doing that, and then you were able to extract the key pair from the enclave, which is bad. But they weren't able to extract Intel's key material. So there's a difference between leaking Intel's key material that's burned in the chip, and then whatever the hell the users are doing at like layer 7 inside of the memory of the chip. If that makes sense. So
you can like pair the chip to the user, but you can't actually like see the data on the chip because that's like layer 7, right?
Who's you?
Like whoever's phone it is, right? So like potentially this phone 123 has like this chip. You'd be able to like pair that if there was some type of leak, but you wouldn't be able to see like the actual data on the phone.
No, like secret network was broken in such that like one of my buddies was like he'd like leaked all whoever owned all those illegal NFTs. Like he just really had all the data. But that's not a fault of that's not like a break in the remote attestation infrastructure. That's a side channel attack that has to do with how side channel attacks. It's a whole separate conversation, like how side channel attacks work with like when you create a cryptographic key material, like what your processor is doing. There's a way to like force it. You can like do volt mod attacks and like try to figure out what kind of secret key is being created. So like, but the point is, the whole trust in the system relies on this. It's way more complicated than this, but it's effectively one key that Intel puts on your chip that's signed by one of their master super secret, not known by NSA keys.
Yep.
And so then Intel will run their little enclave on your chip, and they'll say, "Hey, enclave, I'm Intel, and here, let me prove it to you, and then give me the quote give me the software quote for the stuff running in this enclave, and then I'm going to sign it." And then you would then present that to anyone else in this room and say, "Look, this is signed by Intel. Nobody else knows that key, and so like you could trust me."
Okay.
And because like we don't manufacture the hardware, like no one else can be involved in that attestation like loop. It needs to be the person that burned the key into the chip.
Yep.
It's way more complicated than that, and they've got supposedly like Lattice Grid Plus. If you try to mess with SGX, it'll blow fuses and it will just like destroy the key material on the chip.
Oh wow.
But that's way above my patience level.
Yeah.
So what I'm interested in doing is like, first of all, just talking about this stuff in general. It's cool that OpenBit has a distributed network of nodes that are using SGX, and it's cool that that smart contract platform, the 15 keys are stored in SGX. What's it called? Rootstock. Their keys are stored in SGX somehow, somewhere. But I'd like to get to a place where either the community funds hardware where we can have a trusted setup, where we're all in that room that says NSA is not allowed, and we can all somehow verify that like this was deleted, this super secret private key, and like it's a Genesis situation where we can spawn.
Don't you need to keep it to keep manufacturing hardware? Like you have a fixed run of chips and then destroy the private key?
Well, if you trust, yes, but arguably the first generation of chips could connect to the second gen and like allocate keys on it.
Oh, interesting. Okay.
But if that first key key material is lost, it's hard. How do you rekey everything?
And when you say hardware, do you mean like actual like little like miners or nodes that people would like run in their house, or like?
Yeah, it needs to be like a chip. Like it could be a thumb drive, or it could be. I'm trying to get Ethereum to fund like something more powerful enough that could run a light node in Ethereum.
Yep.
But it could be your phone. The problem is it's expensive to do that stuff.
Yeah.
And so right now there's no community created TEs.
Yep.
Like I don't know if there's a market for that. I don't know if people care, but it's really hard to do because most of the service work is server level. It's really, you want like a Xeon or something like multi-threaded.
Yeah.
And so like we're never going to get there.
Well, I feel like if you had like interesting tokenomics and people could earn some type of like small emission rate, right? Like people would plug it in, people would do it, even if they're
like the thing is, Helium could have done that, but Helium's DNA is their business is like we need to do wireless stuff.
Yeah.
And so to create a little chip that is secure and designed correctly and remotely testable, that's a whole separate business. So like it's just, and this is just new, but for now, what I'm trying to spread is like let's try to decentralize remote attestation, because what's going to happen is Google and Azure and AWS have, hey, use our service.
Yep.
So now you're bringing in another centralized party that will just talk to Intel, and they will be the ones that decide if this is secure or not.
Yeah.
So you all eventually will have a choice as developers, like how do we attest these? Who's attesting this stuff?
Yeah.
Yes, we have to trust Intel, but like just like for a lot of other services, we want convenience, and so we may like incur more risk for more convenience. Like there should be a decentralized way to do attestation.
Yeah.
Whereas if you use Azure today, I'm gonna use the word again, they cock block. You cannot remotely attest yourself. You have to use Azure. Like they literally will block DNS traffic to get the certs from Intel. Like you have to get it from us. So that's directly going to the Edward Snowden's NSA tunnel.
Yeah.
Is what's happening. So like it's happening already. So this is just like more. This talk is more like a here's what's going on. Like think about it.
It's interesting.
So, Any other questions?
I'm scared.
No, but it's exciting because at least there's like people are looking at it now because your phone have had TEs since like probably like before we had sandboxed OSs on our phones.
Wow.
So it's been a thing for a long time. The fact that like people are talking about them now publicly is good because it shines light on all this terrible behavior. So
when you say
it's exciting.
When you say this, you have first gen the chips. You said that Apple is going to sign. Is that all the chips using the same key from Apple or
So Apple is not going to provide you access onto their enclave, nor will Google. I don't know. What is your question?
Yeah, you are saying somehow there's a private key that's going from the manufacturer that's going to sign the key generated from the secret enclave.
I've dramatically oversimplified the process. It's way more complicated than that. Like there's probably about 17 layers of keys, but you can think about it like some like entity or deity, if you will, is like has a key on your chip.
And that's
It's the web server. So you're thinking.
Or sorry, they knows like there's a public key like on your chip, and so
who has a private key? The manufacturer?
Intel.
Is it
Supposedly only Intel.
And they have this key. Is it the same for all the chips or the?
No, each enclave has its own identity, and then which is bound to the hardware itself, and then it also binds the identity of the enclave developer to that hardware. So in order to actually, and that's specific to Intel, to run code in an enclave on Intel, you have to create an RSA 3048, whatever the fuck it is, key, and bind that to the enclave.
So each phone has its own enclave?
Yes, which has its own identity. So like,
Yeah.
they know.
Which is signed by the manufacturer.
They will sign the measurement of what's running in there currently, and then on mobile phones there's a whole process for getting code to even be able to run in the enclave. It has to be signed by Samsung or whoever owns the phone to let you run code in it because it's really privileged. It runs before everything else. So and like the OS can't even look like into the enclave because that's a design.
We could put our private keys in there.
Apple and Google actually, that's the interface you have to them is like some of the secrets will be generated using stuff in the enclave, but you can't like run a Bitcoin node in there.
Yeah.
If we make an open source enclave, we should make them anonymous. Like they should not have identities. They should produce like blind signatures.
But I agree, but the reason they did that is actually not like Dragnet. It's more like because they want you because they're volatile. There's no storage. So you can say encrypt, and it will like encrypt the memory and dump it over here.
Why does that require an identity?
Because let's say someone copies this to another machine, and you only want it to be able, like you only want that to be bound. I guess it is Dragnet. They want it to be bound to you, so like they can only decrypt on that one specific piece of hardware.
I still don't know why. Like,
no, you're right. It could be anonymous. This is for the DRM use case of like I want to know
Right.
who did it.
I'm kind of thinking like, can we make an enclave that you can't use for DRM but could use for interesting
Yes.
things? That should be a design priority for
I
the
agree with
open
that.
source.
There's one other benefit to this system due to the roots in DRM is that you can also attest to a machine's patch level. So I know how up to date your machine is as far as not the OS, but the hardware. Like Intel has firmware updates, right? I can actually attest to then say you're not going to be able to join my club unless you're using the most recent version of Intel's firmware, which is cool. But that requires like Secret Network doesn't care, and so Secret Network will let old nodes join their club that aren't patched that you can then exploit and then leak keys. And so it's you have to actually put a lot of work into maintenance and administration of enclave infrastructure because a lot of these research people will just break the enclaves, and like that's how Secret Network got compromised. Like they didn't update their machines. But most of these networks do not allow you to run your own.
What was the secret?
That like Roger Ver owns all these NFTs that are like.
Right.
But we're approaching this new world where I don't know about for you guys. Do you let users run nodes or do you manage them all yourself?
Currently managed.
Boo. So eventually we're gonna get to a place where you can set up your own infrastructure, and run services. But for now, because like, I don't know why you guys made that design decision, because they don't trust people to run the nodes themselves, maybe.
Because
Or it's hard to do
the
it.
people are retarded.
We are.
Would you have to have some type of, if you had everyone running their own, would you have to have some type of like consensus mechanism within that,
Yeah, I
right?
think so.
So then could you do like a proof of authority, so then with like a ZK proof, so that way people could still kind of be.
And I'm not calling you out, by the way. No one right now. There's no service that lets random internet people join as node operators with Enclave infrastructure,
Yeah.
because people don't know how to even do rekeying. How do you rekey 7,000 nodes inside of SGX? Are we gonna use DKG? Are we gonna? No one knows yet, but it'll happen in 6 months or so.
Yeah.
Anyways, that's kind of it for now.
You should probably make someone pass like a course or something, right? Because even like with Helium, everyone wanted to run validators, right? But it's like, it's complex. Like you have to have some type of technical background to be able to like run a validator, right?
But like, what will happen here is what happened with like military grade encryption.
Yeah.
Like shitty startups will just say we're running it in a TEE.
Yeah.
Because Apple set the stage. If you saw Apple's WWDC presentation, it said transparent, whatever the hell they said,
Yeah.
which is good for us, but
They called it TE transparent.
they didn't use any acronyms. They're smart. They called it like, they used the word transparent, which is
Isn't that
not.
the opposite?
But Tim Cook said it. It's an append-only log. It's not a blockchain.
Oh, okay.
So this is more like a educational thing,
Yeah.
like for you guys. So
Thank you, Ryan.
this is in the Telegram, and these are all links you should check out. This is my favorite paper here. This is probably second, just because Don Song's badass. Check those out. Cool.